Hi everyone, Dennis Foley from Acoustic Fields. Today we're going to talk about diaphragmatic absorption, one of my favorite topics, obviously, right? So I want you to kind of get a feel for a little bit of the science behind diaphragmatic absorption, because this is why it's the most powerful of all the three types. And what are those? Helmholtz, membrane, and diaphragmatic. So diaphragmatic is the most powerful per square foot of all of them, plus the most flexible, okay? Helmholtz is not flexible at all. Frequency specific, you need a lot of units. Membrane, not enough horsepower. Diaphragmatic is really, if you add it all up, is the best one, okay? All of physics, when it comes to acoustics and vibration, if you think of a spring and some mass onto the spring, the whole part of acoustics and physics is based upon the interplay between the mass and the spring. That's what it's all about, okay? And that's why I always tell people when we're dealing with barrier technology that the relationship between vibration and airborne energy is different. And you can't use the same tools, if you will. You can't use foam to stop a garbage truck because it doesn't fit into this. Now, you're more than welcome, if you want to get into the science behind the physics of all of this. And there's lots of books that you can read on that. Get vibrational books, because they'll talk about this a lot. But the goal here is that this system produces what's called a resonant frequency or natural frequency. And it's measurable. It's measurable by using lots of variables, but we won't go into all of that. In terms of sound absorption, which is important to us, when you get a resonant frequency of a system, it's usually the frequencies above that resonant system that are absorbed and those below are not. So you keep searching and designing for a lower resonant frequency. That's your goal, okay? That's what you want to do. We're working on a new design for our carbon series. I'm going to try to get down into the 20s without weighing a ton. That's going to be the issue. But we'll see. We'll see how it goes. We'll keep you posted. So panels with air cavity, the mass and the spring, the same thing. The panel is the mass and the air is the spring, right? So that's what you have to look at. It's the same paradigm. It's the same dynamic as the spring with the weight on it. I know it's a little bit hard to understand, but run with me here. I think we'll get it. So the panel flexing, produces heat loss in the materials inside. That's our standard energy transformation process. That's how we get absorption. So we also get overabsorption when you use building insulation, okay? So the thing we have to realize is that diaphragmatic absorption, resonant frequency, can be calculated with a formula. Somebody spent a lot of time working up this formula, and it's wonderful. And sometime we should probably go into it, but I think it's a little bit beyond the scope of what we're interested in. Resonant frequency, 170 is the constant. Mass, right? Density over depth of the cabinet. So we'll step out of frame here. Let's look at our diaphragmatic absorption, our ACDA series. So we have a cabinet, but the unique thing about our cabinet is we have two front walls. Okay? We don't have one, we have two. Okay, and they're different thicknesses. So think about that. What's that doing? Let's use the word phase. Think about what that's doing to phase. Okay? So our big pressure wave comes through the room and strikes our double walls, okay? Which are not in phase, they're out of phase. So that's going to do something to help us. It's going to slow things down a little bit, right? That's what we want. So then the pressure wave continues and it enters the inside of the cabinet. And what's it going to find when it's inside the cabinet? It's going to find our carbon. Okay? It's going to find a lot of it, 50, 60 pounds in some units. So the pressure inside the cabinet is going to be a lot lower than the pressure of the energy out here, okay? I don't want to use the term vacuum, but you get the idea. There's a big difference between the pressure inside and the pressure outside where the wave was created. So that pressure variance between the cabinet and the wave produces the heat, produces the absorption. So that's how diaphragmatic absorption works. So it's a combination of the density and the depth of the cabinet. So that's why when you work the formula, we get a 10-inch cavity depth for our ACDA 12 series, and then we get an 8-inch internal depth for the 10, which is more broadband. Those were the two frequency ranges I designed for in the beginning. 30 to 50, 30 to 300. All rooms have those. I would venture to say almost 100% of small rooms have those two issues, and that's why we have two products. And most of you that submit your room forms and we look at your analysis and you want to really go after the low end, it's always a combination of 10 and 12. And we have to look at each wall surface. We have to look at which wall surface is producing the 30 to 50 cycle problems, which wall surface is producing the 30 to 300. And then we can calculate how much square footage we need. Our products are very predictable and very consistent. So that's the beauty of a diaphragmatic absorption. So that's the formula. That's how we do it. That's a little bit of the physics behind it, so you get a feel for how diaphragmatic absorption works. It's a pressure-based technology to deal with wave energy. Think of ocean waves. Think of ocean waves and think of diaphragmatic absorption. Now, how do we even increase the performance on the face? We put our foam. So you can get a product that's in the 30s to 6,300. Now that's pretty broad band. And the beautiful thing about the carbon and the foam is the curves really work together. Our curves on the ACDA 12 and the foam are almost identical. That's why they work so well together. So by putting our middle and high frequency foam technology on the face, coupled with the low frequency carbon technology, we get a product that has a lot of horsepower, okay? 1.25, 1.5 dB for every 12 square feet, 30 to 300. It's powerful. It's powerful. Still need a lot of units, especially in these small rooms. Isn't it funny that in order to make a small room sound better, we have to make it smaller because of treatment. We have to take up space. Doesn't sound quite right, but unfortunately, that's what we have to do if we can't knock out walls. If I had my choice, we'd be knocking out all the walls, but my choice does not prevail when it comes to most customers. So anyway, diaphragmatic absorption, a little bit of background. Hope this helps. Thank you. Thank you for watching this video, and if you liked it, please give us a thumbs up. We also have a newsletter that you can subscribe to, so please do that because we offer special price discounts to only those on our newsletter. And then don't forget about our forum. We have started a forum on our own website where people ask questions, and I usually get a chance every couple of days to look at it. There's an interchange between people on the forum, and we'll give you real answers on a regular basis, so that'll help you. Thank you.